All right, let's dive in. Today, we're going to uncover a really beautiful secret that's kind of been hiding in plain sight. It's a connection between the area of a circle and the volume of a sphere that's revealed by just one super elegant idea from calculus.
So, our investigation starts with our first clue, and it lies in the familiar two-dimensional world of the circle.
Now, we all know this one, right? It's probably been etched into your brain since math class. The area of a circle is pi times the radius squared. This is our starting point. Super simple. It just tells us how much space is inside that circle.
Okay, now let's bring in a little bit of calculus. But hey, don't worry, it's not as scary as it sounds. All we're really asking is this. As the circle's radius gets just a tiny bit bigger, how fast is the area growing? In math, we call this the rate of change, or the derivative.
So, when we do that little rate of change operation on our area formula, a equals pi r squared, we get a brand new formula, 2 pi r. Now just tuck that away for a second. Does that ring any bells? 2 pi r. Come on, you've definitely seen that one before. Think back. Bam! It's the circumference.
The rate that a circle's area grows is exactly its own boundary, its own edge. How cool is that? That's our first big clue. The change happening on the inside is literally described by its outside.
So here's the big question. Was that just a cool mathematical party trick? You know, a one-off coincidence? Or are we onto something bigger? Well, to find out, let's jump up a dimension and run the same test on a sphere.
Here we go. Here's our next piece of the puzzle, the formula for the volume of a sphere. It's 4/3 times pi times the radius cubed. This tells us all the space packed inside that three-dimensional ball.
And you guessed it, we're going to run the exact same play we did with the circle. We're going to ask, if we increase the sphere's radius by just a tiny little bit, what's the rate that its volume changes?
And when we apply that same calculus, the derivative of the volume formula spits out a new result, 4 pi r squared. And that formula should also be looking pretty familiar.
You got it. It's the surface area of the sphere. It happened again. The rate of change of the inside of the shape, its volume, is perfectly described by its outside, its surface area. This is definitely not a coincidence.
So let's just look at this side by side. It's undeniable, right? For the circle, the rate of change of its area is its circumference. For the sphere, the rate of change of its volume is its surface area. We found a clear, beautiful pattern. Calculus is showing us one of the hidden rules of geometry. So, okay, we've seen what happens, but now for the really cool part, why does this happen? The reason is actually beautiful, and it's all about how things grow.
See, that derivative, our rate of change tool, is really just asking a super simple physical question. When a shape gets bigger, where does that new growth actually happen?
Just picture a circle in your mind. Now, if you want to make it just a tiny bit larger, where does that new area get added? It's not in the middle, right? No, you're adding it like a super thin little ring right along its outer edge, the circumference. The growth happens right at the boundary.
And guess what? The exact same logic works for the sphere. To make its volume bigger, you have to add a thin new layer to its exterior. It's almost like giving it a fresh coat of paint. That new volume gets spread all over its entire surface area.
And all of this leads us to a really elegant conclusion, a powerful principle that connects the dots between calculus and the shapes we see every day. So, let's recap. The rate of change of a circle's area is its circumference. The rate of change of a sphere's volume is its surface area. And the reason for this is beautifully simple. A shape grows at its boundary. Calculus just gives us the language to perfectly describe that physical reality. So, if you remember one thing from all of this, let it be this simple, powerful idea. The rate of growth of a shape is its boundary. It's this profound idea that the change happening inside something is perfectly mirrored by what's happening on its edge. And this just leaves you wondering, doesn't it? If this incredible connection is hiding in something as simple as a circle or a sphere, what other mind-blowing secrets about growth and change are just waiting to be discovered in the geometry all around us?